So in this example, if we're going to use complex techniques, we don't know how to deal with sine ax. So we're going to have to turn it into an exponential and take the imaginary part. So our first thought would be to write it like this. Now here we have to be careful. Normally we would think of putting the imaginary part outside here. So what's the problem with that? Well, you see, when x is 0, we've got 1 here and we've got 0 here. So we've got a pole at x equals 0, but we can't write this as a principal value because we're integrating from the pole to infinity rather than through it if we do that. So we can't put the imaginary part there. We actually need to put the imaginary part inside the integral in this case. So then we're okay, because then if we take the imaginary part of this, then we get exactly sine ax. Okay. So next thing to consider is, okay, if we're going to use a contour integration technique, then what are we going to do? What kind of contour? Well, we're used to seeing e to the ix and thinking of a semicircular contour, but in this case it's not going to work for two reasons. One, the integral is from 0 to infinity, so it can't be a semicircle, and it's not an even integral, so we can't use symmetry in that sense. So it definitely has to be from 0 to infinity, the integral along the real line. Secondly, if we convert this x to a z, then e to the z is a periodic function with period 2 pi I. So we can have infinitely many poles of this function along the imaginary axis. So we can't use a semicircle for that reason as well. So instead we're going to have to use a rectangular contour. And the rectangular contour which comes to mind is one which looks something like this. Where it's going to be of height the period of this function, so that's 2 pi I. So I'll call this r, and this is r plus 2 pi I. And here we're going to have a pole corresponding to at x equals 0, and then because it's a periodic function we should have 2 pi I later. So it means that we're going to have quarter circle indents around those poles. The contour is going to have quarter circle indents around those poles. Okay, so then we're ready to go. So if we do things properly, we now take the limit as big R goes to infinity, and as okay, I'll call these radius epsilon, and as epsilon goes to 0 of the contour integral around gamma of e to the I a z e to the z minus 1. So we now need to split this integral up into basically 4 bits. So the first integral is from here to here, and that is limit as epsilon goes to 0. And r goes to infinity of the integral from epsilon to r of e to the I x minus 1 dx then the next integral is up here. So now we've got dz equals I y, so simply 0 to 2 pi of so now we've got z equals r plus iy and this integral along here, so very similar to this one, except I'm just doing it in reverse. So expect this integral to be a multiple of this integral, otherwise it's not going to work. But anyway, it's from r goes to epsilon of e to the I, and then along here we've got z equals x plus 2 pi I. X plus 2 pi I is the same as e to the x, so this just stays the same on here. And finally, we've got the integral downwards. So it's the integral from 2 pi epsilon, y equals 2 pi minus epsilon, to epsilon of something similar to this. So it's I times dz is turned to I dy, so I get an I, e to the I. So it's just the z turns into iy, so I get minus ay. dy divided by e to the z turns into e to the iy minus 1. Okay, so I forgot to say limit as r goes to infinity here. Okay, so we've also got that so looking at this integral, I've got e to the iar. This factor here doesn't have y in it, so I can actually take out this factor of e to the iar. That has modulus 1, because everything's real. A and r are real. So that has no consequence. I've got e to the minus y, and I'm only integrating from y from 0 to 2 pi, so that's under control. What I'm really interested in is I've got e to the r on the bottom. So overall, this integrand is going to tend to 0 as r goes to infinity. So this integral here is going to tend to 0, going to give you 0 as r goes to infinity. Okay, so that was the easy bit. Right, so next, as I said, I noticed that this is effectively the same integral as this, except I've got an extra factor of e to the ia times 2 pi I. Reversing this, these limits give me, so I'll just write this thing here is equal to minus then I can take out a factor of e to the ia times 2 pi I, which in other words is just e to the minus 2 pi a. And then the rest is just times this integral here. So I'll call this integral, for convenience, I'll call this I1, and then this quantity here is just minus e to the minus 2 pi I, 2 pi a times I1. And now the problem with these two integrals is that as epsilon tends to 0, strictly they don't exist. But if we take the imaginary part, then the imaginary part, putting the imaginary part inside here, then that just gives us the integral we want, I. Okay, so we're close to what we want. We just have to sort of not worry too much. We just have to take this limit a bit later and not worry too much about the real part. Basically, at the end, we're just going to take the imaginary part of the residues and ignore the real part, which basically doesn't converge. Okay, so basically I1 is closely related to this integral. So we've got, this is I1 and this is a multiple of I1, so that's okay. The last thing to do is this integral here. This integral here also has problems because as epsilon goes to 0, then you've got the limit, well, you've got the limit here is e to the 0, so you've got 1 and then you divide it by 0 again. So again, this integral doesn't exist. But if you take the imaginary part inside, then we can do something with it. So let's, before we do that, let's actually simplify this integral. Okay, so after tidying things up a bit. So this last integral, which I'm now going to call I4. So we want to simplify this integrand, make it look a bit nicer. What we can do is the trick of multiplying top and bottom by e to the minus iy by 2. That will give us something which looks like sine half y on the bottom and then we'll see why we're going to do that. So, okay, I'll swap the limits and put a minus sign. Okay, so I'm going to multiply the top by e to the minus I y over 2. And the bottom also by the same thing. So that gives me this. Right, so if I put a 2 here and a 2 here, then this quantity here is equal to 1 over sine y over 2. Now what I'm now going to do is just take the imaginary part of this. So the imaginary part of this will give me sine I y over 2, or minus sine I y over 2, which is going to cancel this, and the minus is going to cancel that. So if I now just take the imaginary part, I'm basically going to take the imaginary part of all of these integrals eventually. So I just want the imaginary part inside the integrand. The problem is that this, as I said, this won't exist. This integral itself doesn't exist as epsilon goes to 0. But if I take the imaginary part, then that's okay. So I just take the imaginary part. The imaginary part of e to the I y over 2 is just minus sine. Sorry, e to the minus I y over 2 is minus sine y over 2. So that's going to cancel with this. It also makes the integral doable. So then I'm allowed to take the limit as epsilon goes to 0. So I then get the result of 0 to 2 pi of, I've got a factor of 2 here, and this sine y over 2 cancels this sine over y. So I'm just left with this. So I just get, integrating this gives me 1 over 2a, the integral of, okay, so it's e to the minus ay evaluated with a minus sign. So I use that to swap the limits. So 0 to 2 pi, and I end up with so this is not I4, it's the integral of the imaginary part of the integrand of I4 when you do the integral. So I'll just write what I mean as the imaginary part of I4. I hesitate to write the imaginary part of I4 because the integral I4 doesn't really exist. But if I ignore the fact that the real part doesn't converge, then I can just think of it as the imaginary part of I4 and just carry on. Okay, so it's the same thing with this. Okay, so we've got, this is basically what we're trying to find, and we know what this is. So finally, this thing here, we can evaluate using the residue theorem. There's no residues, no poles inside the contour, but on these corners, we need to know the residue, and this will equal I pi by 2 times the sum of these two residues. So we need to work out the residue of e to the a z over e to the z minus 1 at z equals 0. So simple pole, so use the usual simple pole trick, differentiate this, and we just end up with 1 divided by 1, so that's 1, and the residue of this at z equals 2 pi I. Same thing, differentiate this, we end up with e to the z, e to the 2 pi I is 1, and upstairs we end up with e to the, sorry, this should have that I in it. We end up with z equals 2 pi, so we end up with e to the minus 2 pi a. That's the residue at z equals 2 pi I. So, putting everything together, we're taking the imaginary part of everything, so it's the imaginary part of I pi by 2 times this plus this. So that just gives us pi by 2 times 1 plus e to the minus 2 pi a is equal to, we're taking the imaginary part, so the imaginary part is basically what we want, so it's I times this, so it's plus this thing here, I4, which I can just conveniently write like that. And then I just need to rearrange things to get what I want. So therefore I is equal to dividing dividing everything by 1 minus 2 e to the minus 2 pi a, and shifting this over to this side. So do this bit first. And shift this over. So this is the same factor as this, so I just get minus 1 over 2a. We can make this look slightly nicer if we multiply top and bottom by e to the pi a. Then we recognize this as something, it's 2 times cosh pi a, and this is 2 times sine pi a. So it's cosh over sine is coth. So it's coth pi a minus 1 over 2a is the final answer.